So I want to talk about sensitivity in linear programming, by which I mean how much would the solution to a linear programming problem change if we made small changes in the constraints? Right? Let me explain that a little more carefully. First of all, by solution, what I mean is the value of the objective function, right? So by the solution, well, it's kind of an ambiguous term in the context of linear programming. Sometimes you think of the solution as the x values, and sometimes you think of the solution as the value of the objective function. So in this context, I mean the value of the objective function. So if we're trying to minimize cost, then I mean the solution is what is the minimum cost, right? Or if we're trying to maximize profit, right, then the solution is what is the maximum profit we can make. And then the other thing is we're trying to think of how that solution depends on the changes in the constraints. And by the changes in the constraints, I mean the coefficients or the constants in that constraint vector, the vector that gives the constants on the right side of the inequality. So to make it clear, let's consider an example. So consider this example where we're trying to maximize the quantity, the value of the objective function. The objective vector is 3, 4. We dot that times x, right? We're trying to find an x which maximizes this quantity, 3, 4 dot x, subject to the condition that x is all non-negative, and subject to the additional constraints that this matrix, this 3 by 2 matrix times x is less than or equal to these three numbers, right? And this is what I mean by the constraint vector. Right? This guy here I'm going to refer to as the constraint vector. That is, it's the constants which occur in the constraint inequalities, right? On the right side of from a times x. Right? So this is a, this is the constraint vector, this is the objective vector. And then the question I'm asking about sensitivity is how sensitive is the optimal value of O, right? That is the optimal value of this objective function. Remember, we denote the optimal value by O star, right? How sensitive is O star to the numbers in the constraint vector? So in this case, to the 30, 10, and 18. In other words, if we made small changes in these numbers, how would that affect the value of O star, right? The optimal value of O. In a sense, what we're doing is we're asking for the derivative of O star when we regard it as a function of the C vector, right? Or in other words, the partial derivatives of O star with respect to these three variables that represent the values in the constraint vector, right? In the context of solving a linear programming problem, we think of these numbers as constants. But when we're thinking about sensitivity, we're thinking about the sensitivity of O star to changes in these values, then we think of these as variables, right? We think of these as parameters that can be changed from one problem to the next. And we want to know, how does O star vary as we make changes in these values, right? So we're going to answer this question for this particular problem. And the answer, well, the way we'll get the answer is we will actually get a formula for O star in terms of the numbers in the constraint vector. And that'll make it very easy to see how slight changes in the constraint vector will affect the value of O star. So this is what the solution looks like. So over here I have the graph of the inequalities. So we have the natural inequalities, so x and y have to be greater than or equal to 0. So, by the way, I'm thinking that this vector, capital X, it consists of little x and little y, right? So we can graph them as the x and y axes in the usual xy plane. And then in addition, we have three inequalities for each row of the constraint inequality, right? So row 1, row 2, row 3. I've labeled them 1, 2, 3, Roman numerals, right? So here's the line where x plus 5y equals 30, and the first constraint says that x plus 5y has to be less than or equal to 30, so we shade down, and so on. So I did that for the other rows of this inequality. And so the feasible set is this five-sided region in here, It's got 5 corners, right? And of course we know that the solution where this quantity is maximized has to occur at one of the 5 corners. And then furthermore, I showed you that we can visually identify which corner it is by graphing the objective vector. So the objective vector is 3, 4, so I graphed that here. This is the vector 3, 4, and then I extended it out further. So this is the direction where the objective vector is going. In order to maximize the dot product of the objective vector with x, we have to pick the point in this dark blue feasible set whose dot product in this direction, or with this blue vector here, or this green vector, I guess is actually green. This green vector is greatest, and that means we have to pick the corner that extends furthest out in this direction. So visually, it's pretty obvious that this is going to be the solution. The solution is going to be at this point. This is the point that extends out furthest in this direction, right, along the direction of the objective vector. Now, this corner is formed by the intersection of lines 1 and 2, that is, the lines coming from the first and second rows of the inequalities. Line 3 does not play any role in forming this corner. Okay, so we could actually everything is a whole number here. I could just read off the solution, but what I'm going to do for the purposes of analyzing sensitivity is I want to show you how you can compute the coordinates of the corner point using matrix inverse, using a matrix inverse, right? So what I've done here was, since this corner is formed by lines 1 and 2, I'm going to just keep rows 1 and 2 of the A matrix. I'm going to drop row 3. So here's row 1 and row 2 of the A matrix. I'm going to set row 1 and row 2 times x equal to just the first 2 entries over here, and equals meaning that we know that this point is actually on the line where the 2 sides are equal, right? So we're replacing the inequality with an equal sign because we're working on the lines now. And now you know how to solve an equation like this using linear algebra or using matrix inverses. This is now a 2 by 2 invertible matrix. So we can calculate x star, right, the optimal x and y values, by multiplying by the inverse of this matrix. Okay, let me just introduce a little notation. I'm going to use a hat, a with this little caret on top, a hat, to represent this truncated form of the A matrix, where we've left off the third row and we just kept the 2 rows that we need in order to determine this corner point. Okay, so that's a hat. So what we have to do in order to solve for x star is we have to multiply both sides by the inverse of a hat. So we multiply both sides by a hat inverse, and we get this. Right, so so this is x star, and then finally, remember what we're really interested in is how the value of the objective function is going to change. So now that we've got x star, what we want to do is we want to take the dot product of the objective vector 3, 4 dotted with x star, and now what I've done is I've written the whole thing out as in the form of matrix multiplication. If x star is a column vector, and of course 3, 4 is a column vector, then you can take the dot product of those 2 column vectors. An equivalent thing you can do is you can take the matrix multiplication product, where you convert this into a row vector. In other words, you transpose it into a row vector, and then just apply matrix multiplication of that row vector times the column vector x star. And so that's how I've written it out here. I just wrote it out using ordinary matrix multiplication instead of using the dot product. But it's the same thing. It's going to be 3, 4 dotted with this quantity, which we just saw is x star. So this is a formula for the value of the objective function at the optimal corner. And notice that here we've got the numbers from the constraint vector, the 30 and the 10 from the constraint vector, explicitly in the formula for the optimal value of O, right? So this will help us answer the question about sensitivities. What we should do now is just, let's do the calculation. Let's figure out what a hat inverse is going to be, and then we can multiply this stuff out here and see what the formula actually looks like, okay? Okay, so doing the calculation for A hat inverse, I'm just using the formula you learned probably back in high school, right? 1 over AD minus BC times the matrix where you rearrange the entries in A, right? You exchange these two corners and change the signs of these two corners. So this is A hat inverse, which if you multiply the negative 1/4, then you get this, right? And then, so that therefore the value of O star, as we saw, is going to be 3,4 times A hat inverse times 3010. Now what I've done here now is I multiplied these guys out, so we can just express it as actually a dot product, this row vector dotted with 3010. Right? So if I multiplied these two guys out, and I got 1/4, 11/4, and therefore the value of the objective function is equal to 1/4, 11/4 times 3010. So here I'm using ordinary matrix multiplication, but you could also think of this as the dot product between this vector and this one. Writing it this way makes it perfectly clear how changes in the values 30 and 10 would affect the value of the final solution for the objective value. If you increase 30 by, let's say, epsilon, right? If I replace this 30 here by 30 plus epsilon, that means I'm going to be multiplying 30 plus epsilon times 1/4 when I compute this product. And that means that the value of O star will increase by 1/4 epsilon. If I increase the 10 by an epsilon, then that means that I'm going to be multiplying 11/4 times 10 plus epsilon, so therefore the value of O star would increase by 11/4 epsilon. Right? So now we know exactly how much the value of the objective function will increase if we increase the values of these constants here. Right? We know what the rate of change is. Right? So you can say that the derivative of the optimal value of the objective function with respect to the first value in the constraint is 1/4, and the derivative of the optimal value of the objective function with respect to the second value of the constraint is 11/4. Those are the sensitivities. Now there was actually a third entry in the constraint vector, right? There was this 18, but as we saw, the third constraint doesn't play any role in forming the optimal corner, right? In other words, this corner, at this corner, the third constraint is slack. Third constraint does not play any role in forming this corner, so a slight change in the 18, well, that would move this line back and forth a little bit, but it still would play no role in forming this corner. So the upshot of that is that if you make a slight change in the 18, it won't have any effect on the optimal solution, right? So therefore we could say that the sensitivity with respect to this 18 is actually 0. Making a slight change in the 18 will not affect the optimal value of the objective function at all. So finally, we can summarize this by saying that the sensitivities are 1/4, 11/4, and 0, right? The sensitivity is 1/4 with respect to the first entry in the constraint vector, 11/4 with respect to the second entry, and 0 with respect to this third entry. I just copied over the constraint vector over here, right? So the sensitivity is 0 with respect to the third entry. So replacing the 18 by 18.5 or anything small will not affect the value of the objective function at all. But this vector of sensitivities that we just came up with, 1/4, 11/4, 0, this has another important significance. It is also the solution to the dual problem. Let me just go through that, explain why it is actually the solution to the dual problem. First of all, let me state the dual problem. The dual problem would be a minimization problem where we're trying to minimize the quantity, I'll call it P. P equals 30, 10, 18 dotted with some vector y. Y has to be non-negative, and A transpose times y must be greater than or equal to 3/4. Right? So to form the dual problem, we replace maximize by minimize. We exchange the roles of the constraint vector and the objective vector. Right? The objective vector in the dual problem was the constraint vector in the original problem, and vice versa. Right? And then we took the transpose of A, and we changed the direction of this inequality. Right? So this is the dual problem. Now, I'm claiming that this vector here, this vector of sensitivities for the original problem, is also the solution to the dual problem. Well, first of all, let's verify. Oh, sorry, I gotta click somewhere where I don't do something. Okay. Notice that in this proposed solution here, the third coordinate is 0. So, we're kind of assuming here, if that is the correct solution to the dual problem, that y3 should be equal to 0 in the dual problem, right? By the way, that's consistent with complementary slackness, because remember that the third constraint was slack in the original problem, so we would expect that the variable 3 would be 0 in the dual problem, right, in the solution to the dual problem. So if we make that assumption that y3 is 0, then when you multiply y, where the third entry in y is 0, then what happens is these two numbers are not going to matter. They're going to be getting multiplied by 0 when you perform this matrix multiplication. So you can kind of ignore these numbers. You can just focus on the first two columns here, which corresponds to exactly the transpose of A hat. Remember, A hat was the first two rows of A. If you transpose it, you get the first two columns of this. And similarly, I'm going to use Y hat to refer to the first two rows of Y, right? The first two entries in Y, right? So then what happens if you assume that the third entry in Y is just 0, then multiplying A transpose, oops, let me try this, A transpose times Y with the third entry in y is 0 means that these numbers are not going to affect the value of the product, right? They're going to be multiplied by the third entry in y, which is 0, so they're going to disappear. And therefore, when you multiply A transpose times y, right, A transpose times y, you're going to get the same thing as if you simply took the first two columns of A transpose and multiplied by the first two entries of y. And therefore, A transpose times y is the same thing as A hat transpose, right, the truncated form of A transpose, times the truncated form of y. Okay, so this is just the transpose of the first two rows of A, right, that we were using to solve the original problem earlier. Now, what we'd like to do in solving the dual problem is we'd like to find a corner. So a corner occurs when these are not just greater than or equal to, but they're actually exactly equal to some of these values over here, right? So we'd like to find a corner. We would like to set A transpose y equal to 3/4. And now if we do that, keeping in mind that A transpose y is the same as A hat transpose times y hat, we can now use the inverse of A hat transpose to solve this equality, right, to solve this equation. A hat transpose has an inverse which is simply the transpose of A hat inverse, or it's A transpose inverse. It's still an invertible matrix, so we multiply through by its inverse and we get our proposed solution. At least we know now it's a corner. It's the corner where it's formed by taking A hat transpose inverse times 3/4. Right, and this will be where two of the edges of the feasible set and the dual problem intersect. Right? Now, how do I know this is actually the optimal solution? This is the optimal point in the feasible set? Well, remember what we were trying to do was minimize the quantity P equal to 30, 10, 18 dotted with Y. Now again, if the third entry in y is 0, that means the 18 is not going to affect the value of the objective function. It's just going to be multiplied by 0. So this is the same thing as dotting y hat times 30, 10. So I've written that out here. 30, 10 dotted with y hat here. And yeah, I should have written y hat star. Maybe that would have been better. But this is like y hat star. But look, this expression here, which represents the value in the dual problem, it's actually just the transpose of the expression we got earlier for the value of the objective function in the original problem. Right? In the original problem, we came up with this quantity. Right? We said that the value of the objective function was going to be this, that's exactly the transpose of this expression. And when you transpose two expressions, the value is going to be the same. I mean, in this case, it comes out to be a single number. If you transpose a single number, it's the same number, right? So, in other words, P star and O star are exactly the same thing. And if you recall, because of the inequalities we saw earlier, in general, the minimum of the one problem is never less than the maximum of the other problem. So the only way they could be equal is if you've actually found the solution to both problems, right? So therefore, because we know that this value for P is the same as the value in the original problem, it must actually be the optimal solution, right? There's no way it could be suboptimal. So this is the optimal solution to the dual problem. And the thing to remember about this is this principle here, that the solution to the dual problem gives the partial derivatives or the sensitivities of the objective function with respect to the elements of the constraint vector. Maybe I should have said sensitivities, okay? But anyway, the solution to the dual problem gives the sensitivities of the objective function with respect to the elements of the constraint vector. I haven't given you a general proof, but I think I gave you enough that you can see why it's true and why you would expect it to be true in general. One thing I should mention is that these sensitivities can change at different solutions, right? If you change the constraint vector enough, then, let me go back to my graph here. If you change the constraint vector enough, these numbers over here enough, then these lines will slide around enough that you may no longer be looking at this corner, you may be looking at a different corner to be your solution. Once you change corners, then that's going to change A hat. It'll change which rows of the A matrix you want to use, and that in turn is going to influence the value you get for the solution. So these sensitivities are only valid in the immediate neighborhood of the optimal corner that you found, right? If you change the constraints too much, you may end up switching to a different corner, and then the sensitivities may change at that new corner. But the sensitivities should be, in general, they will be valid for a neighborhood, points in the neighborhood of this optimal corner that you found. Okay, so I want to do a case study of how this would play out in a story problem and something approaching a real-life example. This is a problem taken from Mackey and Thompson's mathematical modeling textbook, or informally known as Superfinite, the Superfinite textbook. It's in, let's see, where is this? I think this is in Chapter 5, Section 1, Problem 3, right? So an accounting firm has expanded its client base, and they have to hire new accountants, okay? So they have 100 experienced accountants working for the firm, but they want to hire 50 new ones, right, to take on these new projects that they're getting, right? Now, they're going to hire the 50 new workers over a course of 5 weeks, okay? And they're going to hire a certain number every week, and they're going to start Monday of each week, right? Now, new accountants, as I said, they start work on Monday. It takes 2 weeks to train them, so they have to be trained by an experienced accountant. Each new accountant has to be trained by an experienced accountant for 2 weeks before the new accountant is ready to begin working on projects. Let's see, one constraint here is that we do have to hire a total of 50 new accountants over the course of these 5 weeks, right? Actually, hire and train them over the course of these 5 weeks, right? And then they all have to be ready. They all have to be fully trained by the start of week 6. So actually, if you think about it, that means you actually have to hire the accountants, or they have to start working during the first 4 weeks, because somebody hired during the 4th week is going to require 2 weeks of training. That means they won't actually be ready until week 6. If you hire somebody during week 5, they will not be ready week 6. They won't be ready till week 7. So really, you only have 4 opportunities to hire new accountants, right? So that's going to be the variables. It's going to be how many trainees are hired or how many trainees come on into the firm during each of the first 4 weeks, this training session. 4 variables, 1 for each week. How many new trainees each week? Okay. Let's see, what else do I... Oh, yeah, now, the thing to consider is that if you're trying to minimize cost, and that's going to be the issue here, we're going to want to minimize the cost to the firm of training all these new accountants, right? Other things being equal, it's better to hire the new accountants to have them start working later. If they start working during week 1, you're going to have to pay them for 5 weeks work, right? Whereas if they start working during week 4, you only have to pay them for 2 weeks work, right? Of course, they all have to be working by week 6, so there's not going to be any difference from week 6 on about how high the payroll is. But you could minimize costs by keeping the new hires down during the early weeks, right? So if you hire somebody early, you're going to have to pay them for more weeks, right? So that's where the minimization is going to come in, right? We're going to try to minimize the total amount of weeks that these new hires will be working, and therefore for which they will be paid, right? You can think of it, therefore, instead of thinking of it as minimizing the pay, we're going to think of it as minimizing the number of weeks that the new hires will work. Somebody hired during week 1 is going to work for 5 weeks before everybody's hired. Somebody hired during week 2 is going to work for 4 weeks, and so on. So you can save money by hiring people during later weeks. And finally, while all this hiring and training is going on, there are still projects that have to be completed, right? Projects that are already on the schedule that will have to be completed. So I'm going to assume, for the sake of this example, that they have 30 projects the first week, 50 projects the second week, 111, 182 projects, during the remaining 3 weeks of the training period. So that they have all these projects that have to be completed during each, respective week of the training period. So that means that we're trying to minimize the cost during the training period of hiring these 50 new accountants while still having enough workers available to work on all the necessary projects, right? So we still have to be able to complete all these projects. So these are going to be more of our constraints, right? So one constraint comes from the 50 new workers, and then we're going to have 5 additional constraints that come from the fact that we have to have enough workers to work on all these projects. Okay? Okay, let's see. So this is the formalization, how we set it up formally. As I said, there's going to be 4 variables representing how many workers new workers are hired during each of the first 4 weeks of the training session. The objective vector, as I said, the objective is to minimize the number of weeks that the workers will be paid for during the training period. Right? So if you're hired during week 1, the number of people hired during week 1, they're going to work for 5 weeks, and people hired during week 2 work for 4 weeks, and 3 weeks, and 2 weeks. So this vector, I'll call it O for the objective vector, O dot X tells us the total number of weeks the trainees will be working for during this training period. Then we have these constraints, right? So remember that we have to have enough workers to work on 30 projects during the first week, 50 during the second, and 111 during the third week, and 182 during the fourth and fifth week. Furthermore, the total number of people hired during all 4 of those first 4 weeks has to be at least 50, right? We have to hire 50 new people. Now, how many people will actually be available to work during the first week? Well, we know that we have an existing staff of 100 accountants, right, on the firm. But from that, we have to subtract off the number of new hires during week 1, because each person hired during week 1 requires one experienced accountant to train the new hire. So the number of workers available will be the 100 experienced accountants minus the number of those accountants who are going to be busy training new accountants. So this number, number of available accountants has to be at least 30. Similarly, during the second week, again, the number of available accountants will be the total of 100 that the firm had originally, minus the number who are still training the workers hired the first week, right? Because it takes 2 weeks to train new accountants, so the people hired the first week are still going to be trained during the second week. And in addition, we've hired more people during the second week, so they also have to be paired up with experienced accountants who will then not be available for working on projects. So we'll have 100 minus X1 minus X2, and that has to be at least 50. Now, during the third week, we start to benefit from the new trainees. We have the 100 that we experienced accountants that we started with. Now, by the third week, the X1 number of accountants hired during the first week have now been trained, and they are now available to work on projects. So I'm adding that number in instead of subtracting it. Right? On the other hand, we will still be missing the experienced accountants who are training those hired during weeks 2 and week 3. This total number has to be at least 111, and so on. Right? So you see how we get the numbers for weeks 4 and 5 in a similar way. Right? Notice that week 4, of course, we don't have to subtract off any X5 because nobody was hired during week 5, right? Okay, so these are our constraints. Now, to write these in matrix form, so I'll be able to enter these in Mathematica, what I'll do is I'll just bring these constants of 100, I'll bring them over to the right side, and then I'll write these inequalities in matrix form. So if I bring the 100, this becomes negative 100 plus 30, so I get negative 70, negative 50, 11, 0, negative 18, 50. Okay, these are the constants on the right side. This will be our constraint vector. And then the coefficients on the left side, like the first row, is going to be negative 1, and there's no x2, x3, x4, so those are all 0. And then we get negative 1, x1, negative 1, x2, and then x3 and x4 do not appear, so their coefficients are at 0, and so on. And then, of course, the last constraint that says the total number of new accountants hired is at least 50, that's just all ones. We just add up x1 plus x2 plus x3 plus x4. Okay, so this is what the constraints look like in matrix form. And so here's the constraint vector, here's the objective vector, here's the A matrix, and then we just enter this into Mathematica and solve it. So I'll just give you the result here. Mathematica gives us a solution that the cheapest way to hire the necessary workers, new workers, while still managing to get all the projects done, is you hire 18 new accountants the first week, 7 the second week, none the third week, and 25 the fourth week. Then you'll have to pay these workers for cumulatively for 168 worker weeks, right? If you add up 5 times 18 plus 4 times 7 plus 0 times 3 plus 25 times 2, that adds up to 168, I believe. So that's how much you have to pay them. You have to pay them for 168 weeks of work. And then if you solve the dual problem in Mathematica, you get this. And as we just saw, the solution to the dual problem gives you the sensitivities in the original problem. Okay, so this solution to the dual problem, these are the sensitivities in the original problem, right? So let's just see what these numbers mean, right? So as I said, you can think of these sensitivities as representing the rate of change of the objective function, the value of the objective function, which in our case was the cost, right? The cost of paying all the new workers. It's the rate of change of cost with respect to each one of the constants in this constraint vector. Okay, so let's go through a couple of these. Okay, the first entry in the solution to the dual problem is 0, so that means the sensitivity of the cost, right, the total salary, is 0 to the first entry in the constraint vector. Well, this entry in the constraint vector basically comes from the 30 projects that we had to do. So, for example, if you change the 30, if you increase the 30 by 1, then this would go down. This would go up actually to negative 69, right? So if we want to do one extra project during the first week, that will change this coefficient by, or this constant by 1, right? It'll increase it by 1, and according to the sensitivity, that will have no effect on the salaries. So in other words, if we want to do a few more projects during the first week, that will not cost us any extra money in salaries for the trainees, right? We can handle that very easily without spending any more money. On the other hand, this third entry in the sensitivity vector tells us the sensitivity to changes in the third entry in the constraint vector. So this tells us that if we want to increase the third entry in the constraint vector, that would be this number, the 11 here. If we want to increase that, now what does that correspond to? That would correspond to increasing the number of projects in the third week from 111 to something higher, right? So if we want to do an extra project or two in week 3, then then this number will go up. And this tells us that for every extra project we want to do, it's going to cost us theoretically, it's going to cost us half a week's salary in extra pay for the workers, right, for the new workers. Now, of course, we can't hire half a worker, so this number doesn't exactly make sense in terms of the real life situation. This is a case where the real life situation really has to have integral answers, right? The answers really have to be whole numbers, but we are treating it as if it were a real valued problem where all the numbers could be real values. So it's good. I think it's good enough for our purposes. We can interpret this as meaning that if we want to do 2 new projects during the third week, it'll cost us 2 times the sensitivity of 0.5. It'll cost us 1 extra week of work. Right? So we can do 2 new projects during week 3, but it'll cost us 1 extra week of salary for a trainee. Right? Let me see, jumping to the last sensitivity, this one says that this is the sensitivity with respect to the last number in the constraint vector. So this says that if we want to increase this number 50, now remember this number represented the total number of hires, right? The total number of new accountants we want. So it says that if we want to have more than 50 people added to the firm permanently, right? We want to have more than 50 people on the payroll at the end of this training period, then that's very expensive. That's going to cost us 3.25 weeks of salary for every new employee we want to add, right? That may seem odd. It seems like you could get 1 extra employee just by hiring 1 extra person during the last week, during the 4th week. But actually hiring 1 extra person during the 4th week would take away also 1 experienced worker who would have to train him or her. And therefore, at that point, you may not have enough workers available to handle all the projects, right? So you have to worry about that. Therefore, it turns out it is actually quite expensive. In order to be able to have an extra worker available at the end of this 5-week training period, you're going to have to hire people early enough on that in order to have enough workers available for the 4th and 5th week of the project, when you still have a sizable number of projects to do. Right? Okay, now finally, let me just note that the sensitivities do change. If you make a significant change to the constraints, like if I replace this constraint vector by this one, right? So I change almost all the numbers in the constraint vector. Then the sensitivities do change, right? So the sensitivities themselves are not constant, because changing the constraint vector can give you a different solution to the dual problem, right? Definitely. But nevertheless, these sensitivities should be valid, at least in the immediate neighborhood of the solution we were looking at, right? So if we were trying to hire 50 new workers with these given constraints, then we should be able to make small changes in the constraints, and then the sensitivities will tell us exactly how much cost we can assume we will incur as a result of those changes, as long as the changes are relatively small. By the way, another way to look at this is you can say that if you want to cut costs further, what's the best way to cut costs? Well, the best way to cut costs evidently would be to reduce the total number of new accountants you need at the end of the training period, right? So if you're really desperate to cut costs, then maybe what you should do is reduce the number of new accountants you want from 50 down to something smaller, right? 49 or 48 or something. That would be the fastest way to cut costs, right? That would be the way to cut costs with the fewest changes to the constraint vector, right? You'd still be able to handle all the projects, but you would save, 3¼ weeks worth of salary. Okay, so you can see how the sensitivities are useful in the case of a story problem because they actually tell you something about how to improve your situation, right? They tell you something about hypotheticals, right? How you could either get costs down or how much of a cost overrun you would be facing if your constraints change slightly, right? So they're quite useful for that reason, for handling hypotheticals.